record it. This is lecture lecture 9, right? So if you remember, we were discussing stability of f of x, and if we were able to choose a v which was positive definite, and if v dot is negative semi-definite, then it is stable, and if v dot is negative definite, then it is asymptotically stable in that domain D, right? So this is what we were doing last time. We did an example also, a couple of examples, right? And if we can show that our V is radially unbounded, right? Radially unbounded. I don't know if you remember the definition. I think radially unbounded was V goes to infinity if x goes to infinity, right? Then if this is true, then it is globally asymptotically stable gas, right? Globally asymptotically stable if your Lyapunov candidate function is radially unbounded. And I think we did example, if the x equals to infinity means for all the different cases, so like v is infinity only if x is infinity, and there were several cases like there were some examples, I think 1 over 1 plus x 2 square or something was there where this thing goes to infinity when what was that example? So I think something like this, x1 squared over 1 plus x1 squared plus just want to give that radially unbounded example. So there's an additional condition on V, which yeah. So this x1 square plus x2 square thing, if this v of x, what do you say, is it radially unbounded, this example here? So I know if so let's see, v of x I can write as, if I take x1 square outside, it will be 1 over 1 plus x1 squared, right? It will cancel out from the top. If I just take out x1 squared common from here and here, it will, I can write it like this, right? Now if I say if x1 goes to infinity and x2, what happens when x1 goes to infinity? That means norm, let's say norm is x1 square plus x2 square. That's a norm, right? Second norm of x, mod of x can be. But let's say x1 goes to infinity, not the x2, and let's say x2 is any constant value or something. Then this goes to 0, so it becomes 1, right? 1 plus 0, 1. So even though your x, mod of x went to infinity, this v of x did not go to infinity unless x2 goes to infinity. So this means it is not radially unbounded. Means the figure will look something like this. Like it has circles like this, and says, and then the curves will start opening in this direction. So this is x2 and x1. So x2 it is curves will be, but here after some time this becomes this kind of opens up. There are no closed compact sets. Do you remember our solution where we said that we could make an in the proof we had this omega beta things like that, right? The energy level curves, and in that curve if you are there you will not get out of that curve. So those were closed and compact sets. But if you see here, after some time I will not be able to make those closed and compact sets. It kind of opens up. So if a function is not radially unbounded, then you cannot take that closed and compact set and extend it to the whole space. It will open up somewhere. Yeah. So that's the logic here. So the energy level curves after some time in the direction of x1, because when x1 goes to infinity, the energy curves kind of opens up here, and I won't be able to make some kind of a closed and compact set omega epsilon or omega beta where I can say if you're here energy is negative semi-definite. So the additional condition of radial unboundedness, if you can show that your function is a function like this, half x1 squared plus half x2 squared, this is radially unbounded. Anything goes to infinity, either x1 goes to infinity or x2 goes to infinity or both goes to infinity, that means the norm goes to infinity, this function also goes to infinity. Then in that case your energy curves are like this. You have closed compact set and it will keep increasing as you go in both x1 and x2 direction. But if a function is not radially unbounded, then something like this will happen and it will open up and then you will seize. So you can still prove asymptotic stability in this domain, right? But you cannot say that, one cannot comment about global asymptotic stability, that you start anywhere and you will come to the origin. That is not guaranteed. To guarantee that, your Lyapunov candidate function should be radially unbounded. Okay, so that's the kind of extra condition you have for radial unboundedness. And last time we did two examples, right? We did inverted pendulum example where, if you remember, like our x1 dot equals to x2 and x2 dot equals to minus a sine x1 minus bx2. So this is an example of inverted pendulum. And if we took two types of Lyapunov candidate functions, right? One was v equals to a 1 minus cos x, cos x1 plus half x2 squared, right? For that your v dot came out to be minus b x2 square, I believe. Yeah. So this is what? This is negative semi-definite, right? So this, if you want to do, you have to understand these definitions of what is semi-definite and indefinite. If those definitions are clear, then it will make much more sense because that will govern your transition from stability to asymptotic stability. Okay. So this is a negative semi-definite function because for negative definiteness it has to be 0 when only if x is 0. x0 means both x1 and x2 0. But this goes to 0 at x2 equals to 0. that means it is not negative semi-definite. So all you can show is that this, it enters a set. If it starts in a set, it will never leave this set, but there is no way you can say that. Okay, but I know that this system is asymptotically stable, right? So the Lyapunov condition candidate function that you chose here was not sufficient to show. So you have to choose another Lyapunov candidate function. I think if you remember, we did an example. Second, we chose this v equals to half x transpose px plus a1 minus cos of x1, right? So there p was p11, p12, p12, p22. So basically the whole idea was this has to be positive definite and v dot has to be negative definite, right? So to show that, at the end you have flexibility to choose p11, p12, p12 to p22, right? Such that this is PD and this is negative definite, and we were able to show that, right? If you do that, then actually it was a negative definite thing, and that means it was asymptotically stable. So this is a hard thing, because sometimes you will not get a proper Lyapunov candidate function. What should you do? So, but later on we will have this LaSalle's invariance principle that we will do, which will, even if we have this condition, we will be able to show that it is asymptotically stable. Even with negative semi-definite property, we will be able to show that it is asymptotically stable. Okay. So now for example, if you take a linear system, right? I don't know if we did this in the modern control class. So let's say we have x dot equals to ax, right? And if you remember, the Lyapunov condition of stability for one was the eigenvalues are negative, of course. If A has negative eigenvalues, then system is asymptotically stable. The other condition was, if you remember, was that there exists a P matrix which is positive definite, A transpose equals to, which satisfy this equation, Lyapunov equation, for any cube, positive definite cube, any positive definite cube. There is a solution to P, then the system is asymptotically stable. So how did we do that? So let's say, so that was the condition of stability. Let's see if it satisfies the Lyapunov theory. How did it came actually? So the idea was, let's say we start with a Lyapunov candidate function equals to half x transpose px, because, and P is a positive definite matrix. If it is a positive definite matrix, it satisfies all the conditions of positive definite, right? If this is always positive, V is always positive, and it is 0 only at origin, means all the x's are 0. When I say 0 at the origin, means origin all x1, x2, x3, x4, x5 equal to 0. So it is only 0 when all the variables are 0, otherwise it is not 0, right? So that's good. So if we find v dot, what is v dot? Del v by, so del v by del x into x dot, right? Is transpose into x dot. So that will be, v dot will be, first we take, so it will be half x transpose dot px, and then half x transpose px dot, right? In this case, and both so now we can plug things in. So now if you plug things in, what is x transpose dot? This will be x dot is ax, right? So x dot transpose is x transpose a transpose, so it will be half x transpose a. In fact, you don't need half for that, that is also still a positive. X transpose a transpose px plus x transpose p ax, right? Now you can take out x outside this side, so we have x transpose this side in both the quantities here, right? So it becomes a transpose p plus pa into x, right? And now we know that it is equal to minus q. We started with that condition, right? This a transpose p plus pa equals to minus q. So if I plug in that, it becomes minus x transpose q x. And we know that q is a positive definite matrix. What does that mean? X transpose qx is, which is v dot. This is v dot, right? So it is not equal to this negative. It's negative definite. That means system is asymptotically stable. So you can see that you don't need eigenvalues if that's how the Lyapunov equation came by. So for the linear system. Questions? Let's see if we have any other. Okay, so now we move to that invariance principle theorem that I was talking about. So this is called LaSalle's invariance principle or theorem. Okay, so let's start with this example. X double dot equals to minus alpha x dot minus beta x, okay, where alpha and beta is greater than 0. So we have equation it's a second order integrator, right? It's a second order integrator. So how would you, first thing is to put it into state space form, right? How would you put that? You can choose x1 equals to x and x2 equals to x dot. Then equations of motion will be x1 dot equals to x2 and x2 dot equals to minus beta x1 and minus alpha x2, right? No problem, right? So let's start with a Lyapunov candidate function. What will be like? Okay, your guess. Suggest a Lyapunov candidate function for this to start with.
1/2
V equals to
square
1/2 x square, x1 square plus 1/2 x2 square, right? Simplest Lyapunov candidate function to start with. Okay, so we can find V dot. V dot will be x1 dot plus x2 dot, right? Is that clear? This what I do differentiation here. So basically, whenever let's say I have this, right, V, how do I get this equation from here? So I'm doing a partial, right? When you do a partial of this is 2. So we have 1/2. You take a differentiation with respect to x1, it is 2x1, right? And then you multiply it with x1 dot also with respect to the time, because it is del V by del x into x dot. So you do it for each quantity. So this becomes x1 dot, this becomes x2 dot, and if we see, then what is x1 dot? It is x2. X1 dot is x2, and x2 will be minus, if I multiply this with this one, it will be minus beta x1 x2 and minus alpha x2 square, right?
There are transposes.
Huh? No, it's no transpose needed. Now, one more logic you see, when I chose this simplest candidate function, I'm not able to cancel this and that, right? It's supposed to be cancelled. That will be good. This is an indeterminate term. So if you think I multiply this thing by alpha, beta, right? If I multiply this by, was it alpha and beta? That's how what I chose, right? Or you can, it's right. If this was beta, what will happen? If I chose this to be half beta x1 square, then there will be a beta here. What happens? So that's the logic. Like when you choose a Lyapunov candidate function, always keep that flexibility that multiplying to a scalar is not a, it does not violate any rule. It is still positive difference. So then that cancels out, and then you are remaining with minus alpha. See, our objective is to cancel in terms which are indeterminate, so that you can make a conclusion on it. So it comes out to be alpha x2 square, and alpha is positive, x2 square is also positive. So this is, we can say that v dot is less than equal to 0, negative semi-definite. So we can reach at a conclusion that at least it is a stable system, right? Okay. There is no denying that, right? It's a negative semi-definite. So you can show that, at least you can say that. Now, but let's investigate, because somehow I know that this system is asymptotically stable. So either you find go ahead and go and back and find a better Lyapunov candidate function, a more general one, and maybe, and not guaranteed that you will be successful in showing negative definiteness. But you can do a simple test. So this shows that if that means v dot equals to 0 where? Because ultimately, if everywhere else except at x2 equals to 0, this is negative. So if we have this x1 and x2, right? Or this is x2 and x1, so x2 equals to 0 is what? This line here, right? This is x2 equals to 0 line. So at this line, v dot is 0, right? That means the energy stops changing. Anything other than that, it is negative. That means mostly it is pushing things like this, right? So that's why that is what is happening. So x2 is going to 0. That's what. But let's see at x2 equals to 0 what happens. So when x2 is 0, can we say that x2 dot is 0? Can we say that? Anything constant, x2 equals to 0 means it becomes constant. Not even 0, let's say it goes to 3 or 4 or whatever. That means x2 dot is 0. So let's plug in the value. So this is our equation, right? So we say x2 dot equals to 0 means minus beta x1 minus alpha x2 equals to 0. Now this is 0, right? x2 is 0. So we are saying that x2 dot cannot be 0. This whole thing cannot be 0 until unless x1 is 0. This is not even possible, right? So what is happening is, by this logic, that physics of the system is telling us that system is asymptotically stable actually. Okay, so going x2 equals to 0 implies that x1 has to be 0. Finally this solution will converge to the origin. There is no other set than x1 equals to 0 and x2 equals to 0 where this is met, this condition is met. Okay, so this is a very simple way of showing. There can be bigger problems like this, but that's the case. So based on this, there is a guy called LaSalle, and he made our life more hard. And so we'll give next theorem will be for this LaSalle guy. Okay. So let's see if I can explain this. So generalization of this idea is called LaSalle's invariance principle. Okay, so let's see. So we need some definitions for it. Okay, so we'll say that let xt be a solution to x dot equals to f of x. So this is always we are talking, right? We are always talking about solution of x of t. So a definition, a point P is said to be a positive limit point. So a positive limit point of x of t. So we are talking about a point P, which is, we are saying it's a positive limit of this x of t here, x of t, if there exists Tn such that when Tn goes to infinity, x of Tn goes to P. So basically I'm saying that x, point x, right, there is a limit to that point x. So if I take t to infinity, for that x of t converges to that point P, right? So let's say that's here, I start here and then this is P. So when t goes to infinity, this x of t will go here. And positive because the time scale is positive. You are going from 0 to infinity. Okay? So we are describing because we want to show that the origin is the this is where it converges. So that's why this definition is important. So x of t is a series, right? It's a data point. You have data point, and when t goes to infinity, this point, the x of t converges to a point. Okay, so that point is called, I'm not saying if x of t converges or not, but a point P is the definition. If it happens, then that point P is the limit, positive limit point. Okay. Next definition, the set of all positive limit points is called positive limit set. Now it can happen that there are several of such points. Like it may happen that now trajectory doesn't matter where it starts, it converges to the set, right? So we can have P1, P2, P3, there can be multiple points. So the set of all positive limit points is called positive limit set. Okay. Now, like for example, example can be this. Let's say a point starting here, a point starting here, all converges to this line, right? So this line is basically a set of all those positive limit points. A circle, right? I go there, so basically this circle is also a set of those positive limit points where the line is the point, the x of t is converging, right? So now another definition, a set M is said to be an invariant set if x of 0 belongs to M implies that x of t also belongs to M for all t in R. Okay, so you're saying that if I have a set, right, which is M, and it's just the new definitions of concepts which we learned, like if you are here, you never get out of this set, then that M set between any time, like whether time goes negative or time goes positive, you are there in that set M. Then that set is called invariant set, right? And if you do a slight twist to this definition, if M is positively invariant, if x of 0 belongs to M implies that x of t also belongs to M for all t greater than equal to 0. So if you're going in a positive cycle, we call it positive invariant set. Mathematicians have, generally for us, positive invariant set makes sense because we don't know the negative time concept, right? So, but I think for mathematicians it is very particular which direction you are going. So for us, every set will be a positive invariant set because time is greater than t0 or 0, right? Again, what set? You are in that set, so the trajectory never leaves that set, basically. That set is positive invariant set. Okay? Now, man. Again, another definition. This is all definitions we are cooking up to explain the LaSalle's invariance principle. Okay? So, bear with me. So there is another thing called distance. Distance to a set. So if I say there is a point P here, right? What is the distance to this set? There is a set and I want to find distance from it. So it's defined like this. Distance to a set can be measured by, we can denote it by this thing called distance rho comma p comma m. So there are two inputs, right? One is the point P and the set M which you are trying to find the distance. So you call it P comma M is infimum. So infimum is the lowest upper bound, if you can think of that. Okay. So it's not minimum, but minimum maximum bound. If you have a time varying. So infimum x belongs to M of P minus x. So basically shortest distance. In other words, it means the shortest distance to any, so there can be thousands of points on this, right? So whichever point gives you the shortest distance, that is the distance. That's how we say that's the distance to that set. Like for example, we have path error we find, right? The path error is always the shortest distance to that path. So you draw a perpendicular, that is the shortest distance, and that's how you define distance. Okay? So when I say another definition, when I say x of t approaches M, what does that mean? It means as t goes to infinity. So there is a point, let's say x of t, and I'm saying this guy goes to M, approaches M, right? As t goes to infinity. What does that mean? That means the distance is decreasing, right? If for all epsilon greater than 0, there exists a t greater than 0 such that distance x of t comma m is less than epsilon for all t greater than mt. So what does that mean? That for let's say I'm starting here, right? So let's say I'm starting here, that means the distance is, let's say, epsilon distance, right? So for this epsilon there will be a time interval, capital T, for the, like, how far you start. Depending on how far you're starting from the set, you have a finite time in which the distance will be less than where you started. Exactly, right? So when that's the approaching means, when I'm approaching to a particular point in the space, every time distance is decreasing, basically. That means it is always less than where I started, and that epsilon will keep going to zero, right? And keep decreasing. That means I'm approaching that set. All mathematical way of saying that I'm towards that set. So, okay. So having said that, there is a lemma, I think, here. Lemma 4.1, I think. So lemma is a, like, it's a nice weather before the bad storm comes. So so lemma 4.1 says, if a solution x of t, right, of x dot equals to f of x is bounded and belongs to D for t greater than equals to 0, then basically what does that mean? If it is bounded, that means it is stable, right, at least. So negative semi-definite is a enough criteria to say that a solution is bounded, right? Because it's a solution, right? That means as soon as you show that v dot is negative semi-definite, at least you know that the system is stable and x of t is bounded. So that is what it's saying. If it is v dot is negative, it comes out to be negative semi-definite once it is bounded. That means for t greater than 0, then its positive limit set L plus is a non-empty compact invariant set. Now I don't know if it makes sense or not. So what I'm saying is that, let's say you have this D, right? In this D, I show that my x of t, because in this D your v dot is negative, the semi-definite, right? Because of that, I know that this will not leave this set. So until now we were just saying that, it will keep rotating in this and it never comes out of it. But it's not true. Means if it is bounded, that means it has to converge to a set. It cannot just randomly keep varying and never comes out of it, kind of thing. Even if sinusoidal oscillations are there, it settles down on a limit cycle kind of thing. But it has to go somewhere. It has to converge to a positive. There is a non-empty positive limit set. What was the positive limit set? That when x of t converges to point p as ut goes to infinity, right? So that means there is a non-empty. If that is the case, that means something is there. I don't know how big that is or how small that is, but there is a invariant set where it has to go. It's not that it randomly will be doing something. It has to. Its positive limit set L plus is a non-empty compact invariant set. Invariant set also, like, when it goes inside this, then it will never come out of that M. Furthermore, right? So if you remember the definition, moreover, x of t approaches L plus as t goes to infinity, and that's true by definition, right? That's the so if in this D it is stable and bounded, that means it will somehow converge to this non-empty set, positive invariant set M. Okay, so we'll see how it applies to that LaSalle, but that's the lemma. We will not do the proof and all, but we'll just keep it there. Okay, so that we can move to controllers and we can apply these things rather than being entangled in the proofs. But it's important. It will make your life easy. This. Okay, you understood, right? What was that? Just very simple. If in D, V dot is this negative semi-definite, that means there will be a non-empty positive invariant set M, where x of t will approach to this set. And what we will show from LaSalle's invariance principle, that set, if there are certain conditions satisfied, then it is the origin. In that case, boom, that means it is asymptotically stable kind of thing, right? So if you can show that non-empty set is origin, then your job is done. Even if it is negative semi-definite, we have shown that non-empty set is the origin. And solution converges to the origin, even if it is negative semi-definite. That's the part we have. Okay. So theorem 4.4. Okay, it is the LaSalle's invariance principle. LaSalle. So most of the time you will have to invoke this, right? Because you don't want to waste your time in finding a Lyapunov candidate function which shows negative definiteness. Maybe it is good enough to show it is negative semi-definite and then apply LaSalle's invariance principle on it and then say origin is that set where, okay, LaSalle's invariance principle theorem. Okay, so it says let omega subset of D be a compact set that is positively invariant. Now everybody knows, right, what is positively invariant. Positively invariant is a set where if you start, you don't get out of it. Positively invariant with respect to x dot equals to f of x, then we say let a Lyapunov candidate function v d to be r continuously differentiable function such that v dot x is negative semi-definite. So we are now saying, okay, things are negative semi-definite. If you are able to choose a candidate function which is continuously differentiable and v dot x is negative semi-definite and in omega, okay, let E be the set of all points in omega where v dot x equals to 0. Okay, so E, in our case, if you remember our pendulum example where v dot x was what, minus alpha x2 squared, right? If you remember the previous example. So where is v dot x equals to 0? At x2 equals to 0. So that means E is x2 equals to 0, right? Whole line of x2 equals to 0 is E. So there is a set E where basically v dot x is 0. In this case, v dot x equals to 0 at x2 equals to 0, right? Okay. So you can easily find that out, what that E set is, and then let M be the largest invariant set in E. And this E, now in this case there is one E, x2 equals to 0, right? But there can be cases, examples where there is a origin is, so for example, let me tell you, there will be an example, some problems where this is where v dot x equals to 0, right? And there will be a case where v dot x equals to 0 at origin also, right? There will be certain examples where there are multiple, so E is everywhere, wherever v dot x is 0, and there can be multiple disjoint sets, right? One, a circular trajectory, a straight line, origin. In this case, the straight line is, if you see straight line, that means this point is also the part of E set, right? The origin is also part of the E set, but you're saying what is the largest invariant set? Invariant set is different than the whole x2. In this case, invariant set, if you remember, what was the definition of invariant set? That if you come to if you go inside that, you don't come out of it, right? You stay there, right? And E is not the invariant set. E is just the place where v dot x equals to 0. We are not saying that if you are in E, you will stay there. But within E, there can be multiple sets, and which one is the largest? In case which one is the largest invariant set? I am saying that this is a part of E. This is also part of E, and both are invariant. Tell me which one is the largest invariant set. The circle, right? Not the origin. So you will see that if that happens, trajectories will go to the circle, not stay on the circle. So the theorem says, let M be the largest invariant set in E, then, this is the theorem statement, then every solution starting in omega approaches to M as t goes to infinity. Got it? So what it is saying that, okay, negative semi-definiteness, we start with negative semi-definiteness, right? And then find E where v dot x is 0. And then in that E, find the invariant sets, largest invariant set. And it is saying that the solution will approach to M as t goes to infinity. And if you can show that largest invariant set is origin, then game over. Then job done. That means system is asymptotically stable, right? So as long as we are able to show that M is nothing but the origin. Okay. So proof is there, but let's just.
So that's the case regardless of what the distance is to, like for example, if the initial condition or whatever, this trajectory solution, the x of t was actually closer to the origin, the trajectories will still end up at the circle bigger, because yes. It's interesting. Yep. Okay.
Exactly. Okay. So that's the case exactly. So there's like what I have said. We can say it in words now. So another. This was the theorem, right? LaSalle's invariance principle. So we have, if you are able to show that your function is your layup for that x dot equals to f of x, we have this, right? If we can show that it is negative definite with the layup now coming, which is easier, negative definite. Showing negative definite is harder. Negative semi-definite is a little easier. So
if we can show that it is negative semi-definite, which means system is bounded at least, right? System is bounded, and there will be a set where v dot x equals to 0, whole thing, right? V dot x, that means, and that set is called E. Okay, and let M be the largest invariant set in E. So till E, I think there will be no confusion. Their confusion always will be in applying this theorem will be what is the largest invariant set. So E is not invariant. E is just saying v dot is 0. That does not mean that x is not changing. Invariant set is where once x enters and it stays there. Okay, so finding a largest set M, and the theorem is saying if then every solution starting in omega approaches M. Okay, so that's the kind of crux of this LaSalle's invariance principle, and that like I think we discussed last time, this largest invariant set if there is origin which is invariant, whereas a full straight line or a circular line which is invariant, the trajectory will go to the largest line, and we will take an example pretty soon for that. So the next
Corollary 4.1. Corollary. So here we just saying that it goes to largest invariant set, right? So corollary 4.1 says that let x equals to 0 be an equilibrium point, because stability and asymptotic stability are properties of equilibrium points, right? Equilibrium point. You have to go? Is it an exercise or let's wait?
May I have your attention? May I have your attention, please? An emergency has been discovered in the building. Responsible personnel are responding.
Okay, guys, record. So the theory, this one kind of shows that I think let's continue. The corollary shows that, where is that going? Where was that? Do you remember where I was in here? Corollary, invariance principle. Yeah, here. So there is a corollary, I think, which says let x equals to 0 be an equilibrium point for 4.1 be a continuously differentiable positive solution. So if so that D in which we are computing the solution, right? D has x equals to 0, which is of course the equilibrium point, and it further says that v dot x is negative semi-definite in D, right? That's the normal condition, and also saying that and suppose that our E, right, where x belongs to D such that v dot x equals to 0, right? So that E is the set where v dot x is 0, and if and suppose the additional condition that we are adding now, and suppose that no solution, pay attention on words, no solution. So what is solution? X of t, right? The solution is x of t for this guy. No solution can stay identically in S, identically in E other than x equals to 0.
So only place. So if we can show that where your v dot in E, where v dot x equals to 0, but somehow there is no way the solution just stays in that E. However, if we can show that it goes to x equals to 0, the solutions goes to x equals to 0, then origin is asymptotically stable. Asymptotically stable. Okay, so after finding E, where like if you, for example, the what was the example, x1 dot equals to x2, and I think x2 dot was minus something, right? A bx2 and minus a by something a sine of x1. I think that was the example, right? For this, our v dot x was minus beta x2 square, right? So E is basically x2 equals to 0, right? So if you put x2 equals to 0, means x2 dot equals to 0, right? So we are talking about the solutions now. We know that the lines, the dynamics pushes it to E, right? You are pushed towards the E because everywhere else v dot is negative except on this line. But what we are trying to show that even when you come on this line, there is no way you stay on line but just go to the origin. And that means system is asymptotically stable. So if you see x2 equals to 0 means x2 dot 0 means a minus bx2, this is 0 means 0 minus a sine x1, right? It was sine x1, or I don't exactly remember, but x1 has to be 0. Then only this condition is. So there is no way the solution, the trajectory stays in E, but it goes to the origin. There is no other solution where it can stay still. That x2 equals to 0 is not possible until unless x1 is 0. That is the case. You cannot stay in E until unless you are at the origin. So that's the case. Then that means it is asymptotically stable. Okay. So that's the whole idea here. So I think this example is already kind of clear. There is another example you can take. An example is, let's say you have mx double dot plus bx. This is the equation of a underwater vehicle, something like that. This non-linearity comes because of plus k naught x plus k1 x cube equals to 0. So that's our awesome equation, right? So we can choose same standard, x1 equals to x, x2 equals to x dot, right? That can happen, and then we can choose a Lyapunov candidate function, something like half mx dot. See, I choose m here because I know that this m will cancel out things. If I don't, you can choose some number, a, b, then half k0 x squared plus 1 by 4 k1 x 4. Remember, there is an x cube term, so when you multiply x to it, something will happen. So that's why I'm choosing this Lyapunov candidate function for now. Let's see what will be v dot. V dot will be mx double dot, right? mx dot into x double dot, right? Plus k0 x into x dot plus k1 4 cancels out, so k1 x cube x dot. Remember, x dot is x2. So this is what is that? So k is x dot. So basically I can write everywhere x dot is common, right? See, so we can take x dot outside just for, and then it is mx double dot plus that was a trick actually, I think, right? So k0 x plus kx cube. I think it should be k1 here, right? Sorry, so k1 x cube. What is it equal to?
Looks kind of like your initial.
Yeah, so
question,
initial,
but it
say
doesn't have
this,
that.
this, except this. But if you
Right,
take
yeah.
this side, it becomes minus. So this is equal to minus of bx dot x dot, right?
Okay.
Isn't it? This
Okay,
whole thing
okay.
can be written as minus of that. So it will be minus x dot into bx dot into this x dot. And this comes out to be minus of x dot squared into bx dot, isn't it?
Looks like it.
And I can say that this is always, so this is equal to, see, x dot is nothing but x2. So we
As
can
long
write,
as b is positive, the whole thing's
yeah,
always negative.
negative. So exactly. So this is x2 squared b into x2, which is negative semi-definite because x1 is not appearing in this equation. So that means e, what is my e? E equals to x2 equals to 0. Basically x dot equals to 0. And now see, when x2 equals to 0, that means x double dot should be equal to 0, right? Because x2 is x dot. So if something is constant, that means x2 dot, this implies that x2 dot should be 0. So let's plug, so that means basically this whole quantity should be equal to 0. So if we do that, it comes out to be minus bx dot into x dot minus k0x plus or minus k1 x cube equals to 0. So this is 0, right? Because x dot is 0. Now can we say that when will this be 0? Only when x equals to 0, right? There is any other thing you can say it is 0? So that means x2 means x dot equals to 0 can only happen if it stays at x2 equals to 0, only x dot equals to 0 if x equals to 0. So that means both the largest invariant set m is so the e is, so what is e? E is x2 equals to 0. It's a line. But what is m? M is 0, 0, which is the largest invariant set. So the system is asymptotically stable. You will have time of your life finding a Lyapunov candidate function to show other way, like really getting a Lyapunov candidate function which shows it is negative definite. Means both. So negative definite should have been like this: x dot square minus x squared, something like that. V dot equals to this. Something like this term should have been there to show that it is negative definite. But you have negative semi-definiteness will be easy to show, and then you apply this LaSalle's invariance principle to show that it is asymptotically stable. The actual solution will actually go to 0. So we are saying it goes there, but there is no way it stays there. We have shown that, right? So it comes to the origin. So that's the trick here. Let's take some other example. There's another. So now let's take the alternative example. What if? So we have used the corollary, right? We are showing that largest invariant set is origin. What if largest invariant set is not the origin? Let's take that example and see if that will be fun.
Shift it and make it the origin.
No, I mean, yeah, we can do that, but origin is in the D. So let's say we have x1 dot equals to x2 minus x1 to the power 7, guys. x14 plus 2x2 square minus 10. And x2 dot equals to minus x1 cube. Can you think of linear systems doing this? X to the power 5, x14, 2x2 square minus 10. Okay, so that's the equation. So let me claim something first. Claim. So see, what is this? This equation reminds you of something? These two. these equations? Have you seen an equation of a, so this seems like what? Ellipse seems like, right? Is it ellipse or a circle? It's an ellipse, right? Because yeah, it's a equation of an ellipse. Yeah, power layer different, but I'm saying looks like a surface which kind of reminds you of if x square, if x, what is that, x, yeah, it's not ellipse, but x1 to the power 4, if you say, I could have always say making it y square, something, right? If we talk in terms of x1 square equals to y, then it seems like, anyways.
It might be a cycle, like, because one of the direction is like parabola and one
Mhm.
is, yeah.
So the claim is the set defined by, so it's a set x1 to the power 4 plus 2 x1 x to the power square equals to 10 is invariant. Okay, so I'm claiming that this set is invariant. To show the invariant property, that means if the solution comes in, it doesn't go out of here. So that's how we have to show. So let's see. So let's find d by dt of this x1 to the power 4 plus 2x2 square minus 10 equals to, if I do d by dt of this, what will be that? It will be minus 4x1 cube into x1 dot, right? Minus, plus, no, y minus,
Yeah.
y minus 4 again x2 dot, right? So what happens when I plug things in here in this equation? Let's plug x1 dot in first one, so it becomes 4 x1 cube x2 and, right, sorry, what was that, 4 x1 cube x2 minus, I'm multiplying this with this, so 4x1 cube into x2, so that's x to the power 10, right? 4x1 to the power 10 into a whole shebang inside the bracket thing, right? So what are we doing? We are multiplying this 41x cube with this equation, right? x1 dot is this. I'm computing this 4x1 cube into x1 dot, right? So that happens that way, and then the second equation is multiplied by 4x2, so that becomes minus 4x2 x1 cube and what becomes minus plus 12 x to the power 6 into that shebang, right? So that comes out to be, oh yeah, so that comes out to be this. Now what we can do, if something cancels out, right, this cancels out, this and this are same, so it becomes minus 4x1 to the power 10 into this means this x1 to the power 4 plus 2x2 square minus 10, this plus, was it plus? Should be minus, right? Sorry, minus 12x to the power 6 into x1 4 plus 2x2 square minus 10. So this is just d by dt of that set that we were talking about, right? So now So now we can do, we can take, this is common, right? This and this is common. So we can take minus outside, it is 4x to the power 10. In fact, 4 can be taken outside, right? Minus 4 means x to the power, x1 to the power 10 plus 3x to the power 6 into x1 to the power 4 2x2 square minus 10. Okay. So when if a set is invariant, that means when you go on this, things should be 0. So if when can this be equal to 0? If I'm just computing, so this is equal to 0 when this is equal to 0. So that means x1 to the power 4 plus 2x2 square minus 10 equals to 0. Okay.
When x1 and x2 equals 0 for the first term.
Yeah, means the first term will only be 0 if both x1 and x2 is 0.
I thought that was what
Yeah.
you're trying to prove.
And yeah, if either n or x1 x2 equals to 0, right? So there are two parts here to this. So this quantity will be equal to 0 if either it is at origin or on that surface. On that surface, sorry, not circle, on that surface. Okay. So this was one part. So we just showed that if d by dt of this will be 0 only if is it at that surface and at the origin. Okay. So I have not shown anything yet. My claim is still there that I want to show that that surface is an invariant set. Okay, I haven't shown that. So let's start with that. So I'm saying let's take a Lyapunov candidate function, and this will be used later on. This two arguments, right? So v is x1 to the power 4 plus 2x2 square minus 10 whole square. So let's say I choose a Lyapunov candidate function like this, and v dot will be what? Twice of this, right? x1 to the power 4 2x2 square minus 10, and then doing dot of all this thing. V dot will be d by dt of this, d by dt of this, and d by dt of this is
4x1 cubed times x1 dot.
actually, wait, so this into, yeah, then d by dt of you can multiply that whole this thing, right? This is d by dt of this, so this multiplied by minus 4, so that becomes 8 into del v by del x, and am I doing it correct? Let me think. V dot, if this is this, then v dot is twice of this del v by del x. Eight into this into x1 to the power 10 plus 3x to 6 into 1 multiplied by this, so it becomes square equals to 0, right? So now we know that if this has to be equal to 0 only if either at the origin, and so this is your E, right? V dot equals to 0 so what do you qualify this as? Is this less than equal to 0, or it's always, so this is positive as long as you're not at the surface, right? because it's a square term, it's positive. This is always positive because of the 10 and the 6 even powers. But at origin this is 0, and at surface this is 0. So your largest set V dot where it is 0 is this equals to 0, and x1 x2 equals to 0. So E is this, E is the set, E includes both the sets, right? That this, right? And this. But which one is the largest? This one is the largest, right? It's a bigger set than the origin. So your trajectories will converge to the surface, not to the origin. Okay? So all the trajectories will converge to and you know you if you want to do a linearization and find eigenvalues at 0, 0, you will see that the eigenvalues are positive. That is the reason it will not stay. So it's giving that this LaSalle's invariance principle is kind of including that. So you have origin, which is unstable, but it is you will see that the trajectories are kind of, so if something like this, right? So this goes, this attracts. So this is the largest invariant set also. So all the trajectories will converge. It will be interesting to make a, what do you call it, phase plot of this actually. We should. Do you still have that? Maybe at the end of class we should make a phase portrait. Let's make it. I'm kind of curious now. So PP plane 8. Okay, can you guys give me the equation? So it should be in terms of x1 and x2. Okay, can we change this here? Can we make it x1? Yeah, let's make it x1 and y x2 so that it's easier. Okay, what was the equation? It's here. So the equations were like this. So it's x2, and there's x2 minus x1 to the power 7 into x1 to the power 4 plus 2x2, oh so not 2x2, 2 into x2, 2 into x2 to the power 2 minus 10. Okay, so that's one, and I can copy it. Don't see. Oh, so that is minus x1 cube x1 to the power cube and plus x2 5 plus x2 to the power 5, and remaining the same. Okay, and I don't know what should be the parameters here. 2 minus 4, so let's say minus 4 to 4 and minus 4 to 4. Proceed. What happened? No, I didn't put anything. Quit debugging. Proceed. Oh, I got something here. So let's see what kind of funny surface. Where is the origin? Origin is somewhere here, right? Here, this is the origin. So that's not a circular shape for sure, but I don't know. But maybe we have to increase the surface. Is it looking like something? That's interesting. So I'm not sure how that surface should look like. Equations are correct, right? Plus 2x2 square. So I think this surface here, right? This.
That's probably where it gravitates towards.
Yeah, so it's not exactly like circular. So if you are inside also, I think you should go towards this, right? Yeah, so anyways, so it doesn't matter where you start, you end up on the surface. Even if you start here, you end up here. So highly, can you imagine this from? Yeah. So I'm not saying what is happening to other trajectory, like what happens. So that domain, that's how it looks like. What if these inside one were squares, like x1 square. Proceed. Should be much easier, kind of a circle kind of thing. Yeah, now it's kind of a circle. So that's. No, it doesn't look like a circle. This should be 10. Radius is 10, right? No, it's not a circle, it's an ellipse. So. Anyways, just wanted to see this hypothetical example. So the principal thing is clear, right? The solution will converge to the largest invariant set in that E. Okay, and if there is no other largest invariant and origin is the only, then it goes to zero, and system is asymptotically stable. Okay. So having said that.
Wait, so is the other one where it gravitates towards that surface considered asymptotically stable, or only if it goes straight to?
Going to surface is not asymptotically stable.
Okay, only going to straight to, okay.
Only going to the equilibrium point 0, 0 is asymptotically stable. Okay. Okay, so let's see what we have. So our life is easy because system is what we are using is not time varying for now. So now we have to come up with conditions for time varying systems. So this has all been, whatever discussion we had so far was for what? X dot equals to f of x. Right? If I have to summarize my stability criteria, it will be, you come up with a Lyapunov candidate function, right? And if that v dot Lyapunov candidate function has to be, in case if you are trying to not use LaSalle's invariance principle, v has to be positive definite, continuously differentiable and positive definite, and v dot can be negative semi-definite and can be negative definite depending on how you end up. If it is negative definite, then it is asymptotically stable, right? And if on top of that, if v is radially unbounded, so yeah, so we can categorize things, right? If this is stable, at least sufficient to say it is stable. Asymptotically stable system is a stable system, right? You can bound it, and if it converges to origin, then it is asymptotically stable. And what about global asymptotic stability? Globally asymptotically stable if this as well as v is radially unbounded. Okay, so that's the summary. Now additionally, if sometimes what happens is, if v dot, you are not able to get, so these are sufficient conditions, remember, right? So you cannot say that this system is not asymptotically stable if v dot is less than equals to 0, if this is satisfied. We can say that it is stable, but it's not.
It could still be asymptotic.
It can be asymptotically stable
And
as
you
well.
have to use
LaSalle's invariance.
Right.
So now if v dot is this, then you use LaSalle's invariance principle, LaSalle's, and there you find E. E is your v dot equals to 0, and in that E find your invariant sets M, where and if the invariant set comes to be, there is no other way that trajectories can stay in E unless both the quantities are 0, then it is asymptotically stable basically. That's the kind of summary what, like, I don't know why you guys were scared of all that stuff. This is what I will remember for always. Other things are, underlying things are in math. How do you actually show v dot is less?
Conceptually, what's radially unbounded again? What was the example you used for that?
Radially unbounded is like if v of x is infinity, if mod of x is infinity, right? So what, for example, there were a couple of examples, right? X is infinity means what? Mod of x can be infinity for either x1 is infinity, either x2 is infinity, or both are infinity, right? But in all the three cases, the norm is infinity, right? And when you plug this into Vx, it might happen that if it is not, so it will only be radially unbounded if it is infinity for all three cases. Because what are we saying? Condition is very normal. As soon as your norm is infinity, V of x should be infinity. But there were some cases where we saw that even if the norm is infinity, which is for this case, that let's say x1 goes to infinity, but if the system still goes to infinity, it still does not go to infinity, right? Because there was some condition, I don't know if you remember, it was one was x1 squared over 1 over x1 squared plus x2 squared, right? So in this case, if x1 goes to infinity and x2 goes to 0, x1 goes to infinity and x2 goes to 0, this goes to 1. But the norm is still infinity, you see what I'm saying? So v of x did not respond to that. So that function is not radially unbounded. And radially unbounded means I am not able to put a closed compact set in a global scenario, because where it can attract the trajectory. Your thing will open up pretty soon, like it thing.
Yeah, okay, yeah, I remember the example now. Yeah.
So this kind of opens up here. So you can say something here till in this domain D, but as soon as you keep going out, suddenly it opens up and you're not able to put a closed compact. That was the, if you remember the proof's basis was getting that closed compact set energy curve, right? And if that energy curve you cannot expand further, then you're done. It is not globally asymptotically. It can be asymptotically stable within a domain D until where this is closed, and then you're done. So radially unbounded means you can draw closed compact set anywhere you want, as big or size you want. If they are not radially unbounded, your closed compact sets will be only limited. So closed compact set is the important criteria. Like, can I say my energy is always less than this and this? Here I won't be able to say that after this. Okay? So that was the summary basically for like time invariant systems, right? So now what we are diving in is time varying system and life. You can imagine time varying systems. Okay, and I promise I think next week we should be able to jump into controllers straightforward. So that just to increase some kind of excitement and motivation, we'll do our first controller next. But again, those controllers will need this stuff, because how do you show that my controller is working? Show that V dot is negative definite or something, right? If you are not able to do that, then you don't know. How would you guarantee that your controller is working? Okay. So for time varying systems, now, right? I think I will not do the proof and all, but kind of we will need some more definitions. Because what time is doing is it's screwing up when you start, right? When you start, the behavior changes. So what we want to give definitions is, doesn't matter. Can we give a definition where it doesn't matter when you start and system is still asymptotically stable? And for that there is a new word called uniform. So if I can show that across the time, we can make it that this bound is uniform, doesn't matter where you start, and it's still, I can give a bound which is not time dependent. You can say that system is uniformly asymptotically stable. So that uniform word will add in to our definition. Is it uniformly stable, uniformly asymptotically stable, globally uniformly asymptotically stable, so things like that. So this uniform word will be tied up in the definitions so that we can get rid of that time dependence, because that's not a good, that you cannot say that if you start at time equals to 2 or time equals up to this time interval you will be stable, and after that, that's not a good definition of stability if you are dealing with time varying system, right? It has to, it doesn't matter when you start, this is the uniform bound or this is the uniform property. So how do we deal with that? That is the kind of logic we have here. How can I get with uniform bounds? Okay. So let's get started. So x dot equals to f of tx, and that's our function now that we are dealing with, right? Function of both time and states. And need the signature pages. I have to send the signature pages to her right after this class. So we had 5 minutes only, but anyways, f is defined over this time domain. So time is between 0 to infinity, and this is some domain D, and it takes it to Rn. So it is piecewise continuous, at least piecewise continuous in T, and locally Lipschitz in X, and 0 belongs to, so 0 that I'm talking about, this D, right? The origin is there. So okay, so these are the assumptions we have, and we will not repeat these assumptions, but locally Lipschitz is important as long because we are dealing with uniqueness of the solution, right? And we are saying that x bar is an equilibrium point. And if f of t comma x bar equals to 0 for all t greater than 0. Okay. So I'm just thinking now whether should I start this now, otherwise I will have to repeat it again on Friday.
Repeat is fine.
Huh?
I don't mind repeating.
So let's only in the sake of time, let's stop here for now. We'll start. Otherwise, I have to just to warm up. I have to again start here. Okay. Friday, we quickly can see those questions. But we will try to go over this time varying stability conditions. Okay. So good luck. So I don't know. Any feedback? I know you guys, you have already stated me that you want more practical simulation, but we will have to go through this first to even for simulations to make sense. Right? So you are putting some kind of a crazy looking controller, and you're hoping that this will work. And where if for that controller we have already shown that V dot is negative definite, then you can relax and see the MATLAB actually going there. That's the beauty, right? Because when you design controllers for people, when the rocket, NASA's rocket or UAV something, they will ask you guarantees. Can you guarantee me that this solution, given these kind of certain conditions, will always go there, wherever desired? How do you guarantee that? Nobody will just say, hey, I did simulation for 100 times and it works. You sure? V dot is negative definite, guys. And then you come up with conditions and things like that. So we will also see that even if we are not moving towards equilibrium point, if origin is not the equilibrium point, you can still show the boundedness, that how close you can get to the origin. That is also a very practical application. I can guarantee that you can reach to the origin plus minus 2 something. That also is, as long as you give guarantees that this is what you can get. So that's why this is important, right? And when you write paper, simulation is the last part of that result. One nice looking figure.
Right.
The rest of the thing is showing, and then you say, hey, see, I said in theory it works, works in some simulation. Not vice versa. People who cannot prove have to really take pain in the butt to get their papers accepted. Because then you have to do Monte Carlos and you have to do this, and people, reviewers will never agree. Saying, no, what 100 solution, you have not included these parameters, you have not this, you have not done this experiment outside, it is just simulation. You will have time of your life convincing reviewers if you don't have a proof, mathematical guarantee that this will work. So that's why it is important. Okay?